All right, welcome to section 3.2. What we're going to be talking about here, just you could read it right from the title, is logarithmic functions. And this is where we're getting to something that's like totally new, because you may have seen exponential functions before. And really what's sort of cool about section 3.2 is we're going to tie in a lot of like the worst sections that you liked the least. So that's awesome because, this class is really going to build on itself and we have to make sure we're keeping pace. So intro, in this section, we will learn about a new function called the logarithmic function. The logarithmic function, is the function that is the inverse of the exponential function. So in that last slide, last problem of section 3.1, what I talked about was when we had something like 4 equals 10 to the 1/2 t over 5,730. And I said, okay, we could divide by 10. So we get 2/5 equals 1/2 t over 5,730. And then I said, we don't know how to solve this yet. Well, now we're going to know how to solve that. Logarithms are what's going to get rid of this 1/2. So then I'm left with just that exponent expression. So logarithmic functions. For x being greater than 0, and a being greater than 0, and a not being equal to 1, this right here is our domain. Then, given all that information, then y equals log base a of x. So as long as a is positive and not 1, as long as a is positive and not 1, and x is positive, then y is equal to log base a of x. If, and only if, that's what that double F means, x is equal to a to the power of y. So a couple things here. Notice these bases are staying the same. This is exponential notation. This is logarithmic notation. The bases are the same, but the exponent in an exponential function is the answer to a logarithmic function. This is also f of x is equal to log base a of x. And again, that's read as log base a of x. Now this is not like a to the power of x. A is the base of log. X is the argument of log. And then we also have what's called the natural log. The natural log is the logarithm. Okay, sorry, interesting spelling there. Logarithm of base e. So natural log is just a specific thing where if I have log base e of x, that's the same as just natural log x. So when we see that ln, that means natural log, and it's just log base e. What that also means is if you have natural log of x equaling y, what we can do to rewrite this into exponential notation is you take that base and you go around in this circle. So the base here is e to the power of y is equal to x. This is just some sort of getting familiar with how this works. Those examples, make sure that you go and actually watch them. Pretty important for understanding how to rewrite into exponential notation, since that's part of what it's going to be asking us to do. Properties of logarithms. So just some properties that allow us to rewrite things. If I have log base a of 1, what this is really saying, or what this is going to be, is 0. So log with any base of 1 is always going to be equal to 0. And your reason is because if you think about this circular motion, if I'm writing this in exponential notation, I would go a to the power of 0 is equal to 1. And that's true. Anything to the power of 0 is equal to 1. So that's why this property exists and, is allowed. Log base a of a. So thinking about this circular motion, you're saying a to some power gives me a. Well, the power is the answer to a logarithm. So a to what power gives me a? That would be the first power. So if I have log base something of the same thing, I get 1. Next, if I have a to the power of a log base a of x, what I get is just x. And in that same way, log base a of a to the power of x is equal to x. Both of these are just using the fact that these are inverses. So if these are inverses, which they are, logarithms and exponential functions are inverses. If I have an exponential function raised to a logarithmic function with the same base, those just cancel. If I have a logarithmic function of an exponential function with the same base, those just cancel. The important thing there being that they have the same base. And last, if log base a of x is equal to log base a of y, then x must be equal to y. So these are just some properties for us to use, and a lot of times they're going to help us with rewriting things or solving things. All right, and then what I want to talk about is the graphs. So graphs of logarithmic functions. What we're going to do is create a table and sketch the graph. So if x is 0, well, something to keep in mind. X being 0, we have a domain on a logarithmic function. Our domain as x must be greater than 0. And if you think about this rewriting circular motion, this is 2 to the power of f of x gives me x. So if I want to think about this in exponential notation, 2 to the power of f of x gives me x. So if x is 0, I'm saying 2 to some power gives me 0. Well, 2 to no power would give me 0. You know, if I make this negative, I just turn this over and make it 1/2 to something, which is still not going to get to 0. So this is just undefined. Here I have 2 to some power gives me 1. 2 to some power gives me 2. Again, I'm just using this exponential notation. 2 to some power gives me 4. And 2 to some power gives me 8. Well, 2 to the 0 power would give me 1. 2 to the first power would give me 2. 2 to the second power would give me 4. And 2 to the third power would give me 8. So if I want to sketch a graph of this, I'm going to start with just that, axis. If I'm plotting these points, I have x being 0 is undefined, x being 1, y is 0, x being 2, y is 1, x being 4, y is 2, x being 8, y is 3. So you can sort of see what's happening here is I'm going to go from this was undefined, remember, and through these points, and it will sort of just get really, 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 really slow, but it will always keep increasing. What goes right here ends up being an asymptote. We'll get into more of the graphing so that you get where that's coming from. Now, there are going to be 3 points for you to sort of always remember because we'll use them a lot. So in logarithms, we always have to be using these 3 points, or you always want to be. 1 over a comma negative 1, 1 comma 0, and a comma 1. These are your basic points, where a represents the base. So notice we would have 1 over 2 comma negative 1, 1 comma 0, and 2 comma 1. You can see 2 comma 1 and 1 comma 0. 1/2 comma negative 1 was on this graph. These basic points are what we are going to use to graph logarithmic functions. Graphing logarithms is a lot tougher than graphing exponential functions because the points you pick are sort of not just arbitrary. You can't just pick anything. So getting into that a little bit more. First thing to notice from this graph is that there is a vertical asymptote. At x equals 0. And something for you to sort of be mindful of, when we talked about an exponential function, we said that it was a horizontal asymptote at y equals 0. And an exponential function and a logarithmic function are inverses. Way back when we first talked about inverses in chapter 1.6, we said that in an inverse, x and y are switched. So if I'm switching x and y, our function before had an asymptote at y equals 0. Well, I switched x and y, so now it's x equals 0. The domain is restricted to x being positive, and that does not include 0. The x-intercept is always 1, 0. And again, this is all for a basic function, meaning something that has not been shifted, dilated, or reflected. The graph will pass through the point a, 1. So in this previous problem, a, 1, a was 2. So 2, 1. And all transformations of functions, shifting, stretching, shrinking, these are dilations, and reflecting, are applicable to logarithms. So if I'm going to take f of x equals log base 6 of x, I'm going to use 3 points. A here is 6. So I have 1 over a negative 1, 1, 0, and a 1. So this becomes 1/6 negative 1, 1, 0, and 6, 1. So now when I go to graph this, I have points for me to just plot based off of that base. 1/6 common negative 1, which is like, right here. 1, 0, 2, 3, 4, 5, 6. I'm sorry, 1, 2, 3, 4, 5, 6, 1. A vertical asymptote at x equals 0. And my logarithmic function goes right through. Essentially, this should look like an exponential function that has just been turned because I'm flipping x and y. Now, again, this is the basic function. So, in the examples video, we're going to talk about dealing with some of these reflections, shifting, especially this vertical shifting. That's sometimes a lot tougher. So make sure that you go and actually watch that. But for right now, you have these notes. Make sure you jot down if there was something that you want a little bit of clarification on. Maybe you go check out the optional video, see if it answers it a little bit just for the piece that you're looking for. Otherwise, make sure you bring your questions.